Hello. So this video is going to go through the workbook for the Module 3 practical, in which you were given this blank or relatively blank spreadsheet, and the purpose of the workbook was to take you through the population and analysis of a relatively straightforward state transition model. But the first task of the workbook was a paper-based task, and that was to define the equations or the formulae that you'd need to use in Excel to implement or to estimate the proportions of patients in different health states in different cycles of the model. So we were asked to estimate cells B5, C5 and D5, which are the proportion of patients in the disease-free, recurrence and dead states respectively in model cycle 2, at the beginning of model cycle 2. And so to do that we need to combine the proportions in the states in the previous cycle, so in cells B4, C4 and D4, with the probabilities in the transition matrix. So if we start with cell B5, which is the proportion of patients who are in disease-free at the beginning of model cycle 2, we have to take the proportion of patients in disease-free state in the previous cycle, the end of the previous cycle, and multiply that proportion by the probability of remaining disease-free. So that's cell C18 in the transition matrix. So we multiply by C18. And that's the only way that you can get into the disease-free state, is if you were in disease-free originally. So if you're in recurrence, you've got a 0 probability of moving to disease-free. If you're dead, you've also got a 0 probability of moving to disease-free. So for recurrence, very straightforward. For disease-free, very straightforward. For recurrence, we've got people who were in disease-free in the previous state, B4, multiplied by the probability of moving from disease-free to recurrence. So that's cell D18 in the transition matrix. And we've also got the proportion of patients who were in recurrence in the previous cycle, so that's cell C4, multiplied by the probability of remaining in recurrence at the end of the cycle, and so that's recurrence to recurrence, that's cell D18, and if you're dead, you've got a 0 probability of moving to recurrence, so we don't need to worry about that transition probability. For the dead state, we've got the people who were disease-free in the previous cycle, so B4, multiplied by the probability of dying, given that you were disease-free, so that's E18, plus the proportion in recurrence in the previous cycle, so that's C4, multiplied by the probability of dying, given you were in the recurrent state, so that's E19, plus the proportion of people who were dead in the previous cycle, D4, multiplied by the probability of remaining dead, which is 1, which is cell E20. And so those are our equations or formulae that we'd need to enter into the Excel model to estimate the proportions in each state at the end of model cycle 1, beginning of model cycle 2. So we can essentially just add those in. So it's B4 multiplied by C18 plus C3. No, I'll put D. So we've got to do the previous cycle. So that's B3. So plus C18 plus C3 multiplied by D18 plus D3 multiplied by E18. So that gives us our 0.9, which was what we had in the example for proportion disease-free at the end of cycle 0, beginning of cycle 1. Now what happens if we copy this across to get the recurrent state? So if we look at what happens, we've got B3 times C18. Here we go, sorry, the wrong one. No, I thought it looked a bit wrong. So now we've got C3 times D18, so that's C3 times D18. So what's that telling us? That's telling us the proportion who were in recurrence in the previous year. Sorry, proportion who were in recurrence in the previous year multiplied by the probability of being in recurrence after you were disease-free. So that's the wrong link. So what we actually want is the B3, so it's proportion who were in disease-free in the previous year, multiplied by not D18, which is probability of moving from disease-free to recurrence. Oh yes, it is. We want probability of moving from disease-free to recurrence, so that's D18. And then we want C3, which is the proportion in recurrence, and we want the probability of remaining in recurrence. So rather than E18, we want D19, and then we want proportion who are dead multiplied by the probability of moving from dead to recurrence, which is D20. So that's similar to what we wrote down in the formula. And so you can see that by not using any absolute referencing, when we copy the formula, we're getting mistakes and we're having to adjust the formula manually. But how could we do the formula so that we could just copy it across the columns and also down the rows? So if we go through each item in the formula, B3, so we want the 3 to change. When we copy down, we want the 3 to change, so it's reflecting different cycles, but we don't want the B to change. So we always want to refer to the proportion who were disease-free in the previous cycle. So if we put the $ there, that will help us with that. In terms of the transition matrix, we want the column to change because we're moving from disease-free to recurrence to dead, but we don't want the row to change, so we put the absolute reference in front of the row, and we do that for each of the components of the formula, and that should allow us to take that formula and copy it into there, and so that's worked well. So we've got the 3 prior states, and we've got the 3 probabilities, transition matrix probabilities, that relate to the probability of moving in to the dead state. So it's moving from disease-free to dead, from recurrence to dead, and from dead to dead. Okay. So we can copy across the columns. We can also copy down the columns. So now if we look to take this one for example, we're multiplying the previous proportions in the previous cycle by the probabilities of moving into the recurrent state. So we're wanting the proportion in the recurrent state, we've got the previous cycles multiplied by the probabilities of moving into the recurrent state. So that gives us our base model. So this is basically giving us the proportion of patients in each state at the beginning of each cycle. So the beginning of cycle 0, everyone's disease-free. Beginning of cycle 1, 90% are disease-free, 8% are in recurrence, and 2% are in dead, and so on. Okay. Now, the next stage is to estimate the half-cycle corrected, or make the half-cycle adjustment to those proportions. And the reason we do that is because later on we're going to want to apply our costs and utility weights to the proportion of patients who are in each of these states. So if we say, right, everyone was in disease-free in the first cycle of the model, cycle 0, and we apply the cost, so say $200 is the cost of remaining disease-free for one model cycle, for 1 year in this case, then we'd estimate a cost in the first cycle of the model of 1 times 200 plus 0 times 2,000, which is the cost associated with having a recurrence, and clearly dead, it doesn't make any difference, but it'd be 0 times the cost of 0, because there's no cost associated with being Z. But what does that imply? That implies that the people who moved from disease-free to recurrence, or moved out of the disease-free state during that first cycle, did so right at the end, on the final minute of that cycle. So they all incurred, so all patients incurred $200 worth of costs during that first cycle. But that's an unlikely scenario, that everyone who experiences a recurrence experiences that recurrence right at the end of the cycle. On average, we'd expect that those 8% of patients who experienced a recurrence would have experienced that recurrence halfway through the first cycle. So they'd have spent half a cycle, on average, spend half a cycle in the disease-free state and half of this cycle in the recurrent state. But the way we've set it up here is we're assuming they remain the whole cycle in disease-free. So that's why we apply a half-cycle correction to adjust the proportions of patients in the different health states for the fact that when you're moving between a health state, you move on average, we assume, halfway through. So to estimate that equivalent proportion, we take the proportion of patients who remained in the state for the full cycle, so that's this proportion here, so 0.9 were in the state at the beginning and the end of the cycle, so they experienced a full cycle, so we multiply that proportion by 1. And then we estimate the proportion who left the cycle, so that's the proportion who were in, so we put it in brackets, the proportion who were in the state at the beginning of the cycle, minus the proportion who were in the state at the end of the cycle, so that's the proportion who left, and we assume they left halfway through, so we multiply that proportion by 0.5. You can see we get an equivalent proportion of 0.95 patients who remained in disease-free state for the full cycle. And we can copy that formula across, and you can see now that we've got equivalent proportion of 0.04, so half of this 0.08 who remained in the recurrent, who were in the recurrent state for a full cycle, and 0.01, which is half of 0.02, who are in the dead state for the full cycle. So that's one way of writing the formula. A slightly easier way is to take the average of the proportions in the state at the beginning and the end, and that will give us the same result. So we can just take the proportion who are in at the start of the cycle plus the proportion we're in at the end of the cycle and divide by 2. And we get the same result, and we copy that across, and again we get the same results. So now we can copy that down over 10 cycles. So here you can see we've got our 10 cycles, and now we've got a half cycle corrected model, which gives us the equivalent proportion of patients who were in each state during each cycle. And one of the questions on the workbook was, why don't we estimate the half cycle corrected proportions for the 10th cycle? And that's because the 10th cycle is actually the 11th cycle, because we started with cycle 0, and this is giving us the proportion of patients who are in each state at the end of the 10th cycle. So we need the people who are in each state at the end of the 10th cycle, so we can estimate this half cycle corrected adjustment for the 10th cycle of the model. So we've got our proportions. Now we've got the relatively straightforward process of multiplying the proportions in each state by the relevant cost weights. So the workbook tells us that people who are disease-free and assigned to drug B are receiving the costs of drug B plus these additional costs of just being in the disease-free state, which may be monitoring or surveillance costs over each year that they remain disease-free. So we have to combine the cost of the drug and the cost of the surveillance. So we've got F3 multiplied by the cost of drug B, H17, plus the cost weight for the disease-free state. And so that gives us the proportion of patients who are disease-free incurred an average of $285 over the first cycle of the model. Now we want to be able to copy this formula down, so we want to make the H17 and J17 absolute references, but we just need to make the row rather than the column the absolute reference. So that means we can copy that formula down to the end. So here we've got the proportion disease-free in cycle 9 multiplied by the cost weights, the relevant cost weights. And we do the same thing for recurrence, so we can multiply the proportion in recurrence by the cost of recurrence, so we make that an absolute reference. I just pressed F4 by the way there to make an absolute reference. So we've got the cost of disease-free, the cost of recurrence for each cycle, so we can estimate the cycle costs as the disease-free plus the recurrence costs, and copy those down. And we get a total cost is the sum of those costs across each cycle. So that's our total costs. We do the same thing for QALYs, so it's the proportion disease-free multiplied by the utility weight for disease-free, and the proportion in recurrence multiplied by utility weight for recurrence. And then we can estimate the total as, so these are the total QALYs gained per cycle. So it's the QALYs gained by people who were disease-free, the QALYs gained by people who were in recurrence. And then we can copy all of that down, and we forgot to make them absolute references, so we have to go back. And, it's only the recurrence, so we should have made the recurrence an absolute reference. And there we go. So then we can just actually copy this formula into here. So the total QALYs for people receiving drug B, 6.78, total cost 5,329. So we'll come to the discounted issue in a minute, but first of all we'll just essentially go through the same process to populate drug A. The only thing that changes is the transition matrix. So here we know that we've got an estimate that the treatment effect of drug A relative to drug B is that the risk of recurrence is 0.8 of the risk of recurrence for people receiving drug B. And so we need to estimate the transition matrix. And so the effect is on the probability of moving from disease-free to recurrence. And so we're saying that the probability of disease-free to recurrence in drug B is, in drug A, is 80% of the probability, or 0.8 of the probability of, so it's D18 multiplied by H37, and that gives us the probability of recurrence in the word, but we're told that the probability of dead remains the same, so 0.02. Now each row here has got to sum to 1, so we can put in a little check to make sure they sum to 1. So at the moment it's not summing to 1. So the only empty cell is the probability of remaining disease-free. So if we don't experience a recurrence and we don't die, we remain disease-free. And so probability of disease-free is just 1 minus those two. We still can't move from recurrence to dead to disease-free. We can't move from dead to disease-free. We can't move from dead to recurrence. If we're dead, we remain dead. And we're told that you only receive either drug until you experience a recurrence, and so the probability of recurrence doesn't change either, and so we link those probabilities back to the original transition matrix. And the reason I've linked them is because if I wanted to test the impact of, say, a change in the probability of dead, given that you have got recurrence, I need to change this transition matrix and it will feed through into this one without having to check that I've changed both recurrence transition matrices. Now, here we go. Actually what I should do is just copy that across, so we've got the absolute references. Now I can just copy that formula into here, and it will be wrong to start with because it's referring to the wrong transition matrix, but I can just copy those, or just drag those linkages down to this transition matrix, and now we've got the right linkages, and we've got the right formula with all the right absolute references. So we can copy it down, and we can copy it across, and straight away we've got the baseline model. And what you can see here is that the impact of the transition matrix, or the change in the transition probabilities, by year 10, or the end of year 10. For drug A, 0.414 patients are dead, whereas in drug B we've got 0.458. So you can see the impact in terms of progression through the model. We can apply, again, copy the half cycle correction formula down, so that's easy, and we can actually just copy all of this down. So now just to give a check, so if we look on that one, so we're multiplying the proportion of disease-free by the utility weight for disease-free for patients receiving drug A. So it's exactly the same model, just different inputs in terms of the transition matrix. So again, we can just do the sum. So we get the total costs. Now what have I done wrong there? I have copied the linkages for the costs, and I'm still applying the cost for drug B. So really I need to apply the cost for drug A to the cost formula. So if we do that and copy that formula down, we can see that we get higher costs for patients receiving drug A. And so from these data, these four outputs, the costs and the qualities for drug A and drug B, we can estimate incremental cost effectiveness ratio. So the cost difference is the cost of drug A minus the cost of drug B. It's 5,583, and the quality difference is 7.02 minus 6.78. So we've got a quality difference of a quality gain of almost a quarter of a quality over the 10-year period per patient. And so we can estimate the ISA as the difference in costs divided by the difference in qualities, which gives us an ISA of almost $24,000 per quality gain. So the final component of the model is to allow for the discounting of both the costs and the qualities incurred or gained during each model cycle. And the reason we do that is different for costs and for qualities. So for costs, if we take year 10 or cycle 10 as an example, what we're saying is that in year 10 we're expecting to incur just over $500 worth of costs, but we're looking at that from the perspective of the current or the present time. So $506 in 10 years time should be worth a lot less currently, because we can invest, we can make a real rate of return on money that we invest now in preparation for the money that we're going to need to spend in year 10. So you can think about it in terms of economic growth, that economies grow each year in real terms, and we need to reflect that in how we put a present value on the costs that are going to be incurred in future years. So to do that, we take the total costs incurred in each cycle of the model, and we divide that by 1 plus the discount rate. So discount rate here is 5%, so 1.05, and make that an absolute reference so we can copy the formula down. And we take the discount rate to the power of the cycle or the year in which the costs are being incurred. So in this case it's in cycle 0, and so we can copy that formula down, and so we can see here, so let's just get rid of these decimal places. So we can see here that if we expect an annual real rate of return of 5% on dollars available in the present time, that $326 now will be worth the equivalent of $506 in 10 years' time. Now with qualities, we can't invest or expect to make a real rate of return on qualities, but what we invoke is the theory of time preference that essentially says that we'd rather have quality gains, we'd rather have any sort of intangible gain now rather than having to wait up to 10 years to experience those qualities. And so we're applying, in this case, the same discount rate to qualities as we apply to the costs, because that's what the Australian government or Treasury has said that we should do. different countries or different governments have different perspectives on what's the appropriate discount rate and whether we should be applying the same discount rate to costs as to QALYs. But in Australia, we're instructed by the government, when undertaking evaluations from a government perspective, to apply an equal discount rate of 5% to both costs and QALYs. And so we take the total costs in each cycle, again divided by 1 plus the discount rate, make an absolute reference to the power of the cycle. Oh, we've got a formula error, so we've got a double equals there, so yeah, we can accept that amendment, and so we copy that down. So we've got our total cost discounted for each cycle, our total QALYs discounted for each cycle, so we can copy the sum cycle across, and that gives us our discounted costs and discounted QALYs over the 10-year time horizon. And we can just copy that formula down for drug A, sorry. So we've got our total costs and QALYs here. We can again estimate the cost difference between drug A and drug B and the QALY difference. And you can see the QALY difference has decreased, and so has the costs. And then we can estimate the ISA as the cost difference divided by the discounted QALY difference. And see the ISA has increased, and that's because the effect of discounting has been greater on the difference in QALYs than it was on the difference in costs. And so we get a slightly increased ISA. So that's the end of the workbook for Practical 3. If you've got any remaining questions or issues you want to discuss, feel free to post them on the discussion board in the first instance, and then we'll go from there to resolve those issues. Okay, so I'll see you for Module 4.